In cell 1, we're making the smallest possible call to the OpenAI Responses API using a single text string as input. We start by importing load.env from .env, which loads environment variables from a local .env file. This matters because it keeps secrets like API keys out of your code. Next, os.getEnv OpenAI API key reads the key from your environment, and we pass it into OpenAI API key to create a client object, which is our main handle for talking to the API. The key line is client.responses.create. We choose the lightweight model GPT-5 Nano and provide input what is 2 plus 2, which is the simplest request shape. Finally, print response output text prints the model's final text answer. When you run this, you should see something like 4, and that confirms your authentication, model access, and request flow are all working. In cell 2, we switch from a single string prompt to a chat-style format, but we still use the same client.responses.create method, so the API surface stays consistent. Here, messages is a list of dictionaries where each dictionary has a role and content. The system role sets behavior rules like, you are a concise tutor, and the user role contains the actual question. This is important because system instructions act like ground rules, shaping tone and style without you having to repeat that guidance in every user prompt. When we pass input equals messages, the model interprets it as a conversation, and it will usually respond in a way that follows the system direction. So you'll likely get a short, direct answer. The output is printed the same way with response.output text, which shows that whether you provide a plain string or a message list, the response object gives you a clean final text field to display. In cell 1, we demonstrate streaming, which means we print the model's output gradually, as it is generated, instead of waiting for the full response. We start by importing OpenAI and creating a client, which is our connection to the OpenAI API. The key line is client.responses.create stream true. Setting stream true tells the API to send back a sequence of small events, kind of like text arriving word by word or character by character. Then the for event in stream loop listens to those events, and we only print when event.type equals response output text delta, meaning here's the next chunk of text. Notice how print event delta, end, and flush true avoids new lines and forces the console to update immediately, so the text appears smoothly in real time, and the final print just adds a clean new line once streaming finishes. In cell 2, we show how to keep conversation context across separate API calls so the model can remember what happened previously. First, we call client.responses.create and store the result as R1. The important idea is that R1 contains both the generated text and an identifier R1.id for that response. Printing R1.output text shows the joke the model generated, which becomes the shared history we want to reuse. Next, we make a second call R2 and pass previous response ID equals R1.id, which tells the API, continue the conversation from that earlier response. Because of that link, the prompt, explain why it's funny, makes sense. Without the previous response, the model wouldn't know which joke we mean. When we print R2.output text, you should see an explanation that references the earlier joke, like identifying a pun or double meaning, confirming that the context was successfully carried across calls. This snippet demonstrates how to make the model return predictable, typed JSON by combining the OpenAI SDK with Pydantic. We start by importing OpenAI and base model, then create client equals OpenAI to talk to the API. Next, we define a Pydantic model called answer, which is basically a schema that says what fields we expect, a question string, a result integer, and an explanation string. The key idea is that this schema acts like a contract. If the model's output doesn't fit, parsing will fail instead of silently giving you messy text. Then we call client.responses.parse, which asks the model to respond and immediately parses the response into our schema. Notice how input contains two messages, a system instruction, return structured data, and a user request, compute 2 plus 2 and explain briefly. The important parameter here is text format equals answer, which tells the SDK, make the output match the answer model. After the request completes, resp output parsed gives us a validated answer object stored in data. From there, we can safely access fields like data result, knowing it's an int, and print data result should display 4. The main takeaway is that structured outputs make your code more reliable because you can treat the model response like a real data object instead of guessing how to extract information from freeform text. This snippet demonstrates end-to-end tool function calling with the OpenAI Responses API, where the model can ask your code to run a real function and then use the result. We start by creating an OpenAI client, then define a single tool named add using a JSON schema-style parameters object, which tells the model it must provide two integers, a and b. Next, we implement the actual Python function add a and b int, which returns the sum, and we prepare input list with a user message that explicitly requests using the tool. The first call, r1 equals client.responses.create, lets the model propose a function call. We then append r1 output back into input list, so the conversation state includes the tool request. After that, the loop checks item.type equals function call and item.name equals add as a simple safety guard to ensure we only execute the expected tool, parses item arguments with json.loads, computes result, and appends a function call output tied to the same call ID. Finally, r2 equals client.responses.create runs a second model pass here using GPT-5 Nano to produce the user-facing response from the tool output. And instructions is reply with the final numeric answer only, explains why the printed output is just 4.